In the last chapters, we tested means. Now we move to proportions, the yes or no world. Today we learn when the normal approximation is good enough, how to write the hypotheses correctly, compute the test statistic, and decide using either the p-value or the critical value. We'll also build confidence intervals and plan sample sizes. Think of this chapter as the proportion addition of what we already mastered for means. Our course manual uses the rule bigger than 5. Some textbooks ask for 10 because they are more cautious about the normal approximation. The idea is simple. We need enough yes and no's for the sampling distribution to look smooth. If you only have a handful of successes, the distribution of p-hat is still chunky, like popcorn instead of a bell curve. For proportions, everything revolves around counting how many yes we observed out of n. We compare the sample proportion to the null proportion using a z-score. Notice the standard error uses p0, not p-hat. That's one of the classic mistakes students make. The tail always follows the direction we want evidence for. If we hope to show the proportion is bigger, we choose a right tail. If we hope to show it is smaller, we choose a left tail. If we just want to check whether it is different, we choose two tails. Remember, the null always gets the equal sign, and the intention sets the direction. The p-value measures how surprising our sample result would be if the null were true. Tiny p-value means the result is unusual under the null and pushes us toward rejecting it. Always match the p-value to the correct tail. Think of the p-value as the surprise meter. The smaller it is, the more your eyebrows go up. The critical value method is the old-school way of testing. Instead of computing a p-value, you draw a line in the sand and see if your test statistic crosses it. Right tail uses positive z-alpha, left tail uses the negative version, and two tails use the symmetric plus or minus values. It's like checking whether your z-score trips the alarm or not. The image shows the two rejection regions for a two-tailed test. The mayor claims at least 65%, but the student group thinks it is lower, so we use a left-tailed test. The sample proportion is 0.59, which gives a z-score of about minus 1.78. The left tail p-value is about 0.038, below alpha 0.05, so we reject the null. In plain English, the data suggests the mayor is overselling home ownership. Here we just want to know if the peanut allergy rate is different from 2%, so we use a two-tailed test. Our sample proportion is about 0.0275, which gives a z-score around 1.07. The two-sided p-value is about 0.28, well above alpha 0.05, so we fail to reject the null. In plain English, our sample does not give strong enough evidence that the allergy rate has changed from 2%. Be careful about how you interpret a confidence interval. The confidence is in the procedure, not in this one particular interval. Think of it like tossing a wide fishing net. Most casts will catch the truth, but any single cast might miss. A confidence interval is like giving a smart guess with safety padding. In this case, the padding tells us the defective rate is probably somewhere between 4 and 10%. Life would be easier if everything came with confidence intervals. Imagine dating with a label that says 95% chance of being emotionally stable. To plan the sample size, plug the pilot estimate into p-hat-naught. The larger the standard error you expect, the larger the sample you will need to hit your target margin of error. And always round up. If a pilot estimate is not available, use 0.5 instead for a conservative sample size planning. With an estimate, we plug in p-hat-naught and get a smaller sample size because we use the actual variability. Without an estimate, we play it safe with p equals 0.5, which gives the largest possible variability and the largest required sample size. It's like budgeting for groceries. If you don't know what you want, assume the most expensive options. Life is full of uncertainty. Statistics just admits it out loud. In real life, we never know exactly what's coming next, and in hypothesis testing we never know the truth for sure either. We just make the best decision we can with the evidence we have. It's basically adulthood, but with formulas.